Okay, back with example 6.2, 6.2, drag on a barge. Where we left off, we had established which way the barges, or which way the tugboats are pushing on the barge. Uh, Tugboat one is pushing with a force of 270,000 newtons directly along the x-axis, and tugboat two is pushing with a force of 360,000 newtons directly along the y-axis, and we want to know essentially what the acceleration of the barge is given to us, and we want to know what the drag force of the of the barge is. So we've got the input forces, and they should produce ideally a certain acceleration. We have the actual acceleration given in the problem, and the difference between the actual acceleration and the acceleration that we should be able to get based on the forces with which the tugboats are pushing the barge, that is due to the drag on the barge. So basically the barges are putting enough force, or sorry, the tugboats are putting enough force into the barge to get you an acceleration that's considerably larger than the actual acceleration. And the actual acceleration is smaller than it theoretically should be because of the drag. Okay, so essentially what we want to do is find out how much drag there is on the barge by comparing the forces that are actually being put in to the forces that would be necessary to produce the actual acceleration. We can do a free body diagram like so. All of these forces are in the plane of the water, that is the horizontal plane, the plane of the paper, in other words. And so we've got force one pushing directly along the x-axis, and we've got force two, which is a little bigger, pushing along the y-axis. And then we have the force of drag, which is pushing directly against the direction in which the boat or the barge will want to move. The barge, of course, will want to move in this sort of direction here because of the two forces pushing on it. But the force of drag is what FD is, and that's pushing directly opposite in direction. So the weight and the normal force of the barge are irrelevant here. They would be coming straight up and down. They're irrelevant because the barge is not accelerating in the up or down direction. So the weight and the normal force must cancel each other out. There's no net force in the up and down direction, and therefore there's no acceleration, and therefore there's no net force, and around and around and around. We can look at this as a right triangle because we've got F1 in the x direction and F2 in the y direction, and the resultant force of F1 and F2 can be considered, can be thought of as F applied. That is the amount of force actually applied by the tugboats. Okay, so that's just F1 plus F2 in this case. That's counteracted by the force of drag, which points in the opposite direction, to the direction of motion. In this case, the barge is going to be the system, so we're interested in the external forces acting on the barge, which would be essentially the tugboats and the drag. So here we have tugboat one, tugboat two, and the drag. You can find the magnitude and the direction of the applied force just by using the Pythagorean theorem, because like I showed, force one and force two make a right triangle. So for the applied force would be the hypotenuse. And so that is just the square root of F1 squared plus F2 squared, which works out to 450,000 newtons. So the applied force is 450,000 newtons. The angle at which that force operates can be found from the inverse tangent of the y term over the x term. So that's inverse tangent of 360,000 over 270,000, or the inverse tangent of 1.33 repeating, which is 53.1 degrees, which they told us in the diagram at the beginning. But if we didn't know that, we could figure it out from this. Okay, so we basically confirmed it here. Now, the applied force is, notice, the total force that the tugboats actually apply to the barge. Some of that applied force is overcome by drag, and some of it goes into the net force that actually produces the acceleration. And so we can represent that like this. The magnitude of F applied is equal to the total of FD, the force of the drag, plus F net, the force that's left over after subtracting out the drag. So in other words, F applied is F net plus FD. F net is going to be mass times acceleration, though. That is the mass times the actual acceleration that actually occurs. And we know both of those terms. We know that the mass is 5 million kilograms, and we know that the acceleration was 0.075 meters per second squared. So mass times acceleration for the barge gives us an F net of 3.75 times 10 to the fifth, or 375,000 newtons. And so rearranging this equation to solve for FD, we just get FD, that is the force of the drag, is equal to the applied force, that is the force that the tugboats actually apply, minus F net, that is the force that actually manifests itself in acceleration. So the total actual applied force minus the force that we can actually see taking place as acceleration is 450,000 for F applied, which we got up here, and minus 375,000, which we got as F net in the last step here. And that gives us 75,000, or 7.5 times 10 to the fourth newtons for the force of drag. And the orientation of the drag, well, it'll be exactly 180 degrees opposed to the angle at which the barge is moving. And so the angle of the drag will be 53.1 plus 180, or 233.1 degrees versus the x-axis. Or if you want to think of it this way, 53.1 degrees south of west. The angle at which the barge is moving is 53.1 degrees north of east. And so the opposite direction could be considered 53.1 south of west, or 233.1. All right, so that was an interesting example. Another thing that we can do with applying Newton's laws is acceleration directly up and directly down. And the most common instance in which most people experience that would be in an elevator. You've probably noticed, if you're in an elevator, especially in a taller building where they tend to move faster, when an elevator first starts moving upward, you can feel, you basically feel like you're getting heavier. You can feel the floor of the elevator pressing up on your feet, which makes you feel heavier. And on the other hand, if you're going down, when the elevator first starts accelerating in the down direction, it almost feels as if the floor is dropping out from under you. And essentially that is what's happening. Your body has a certain amount of inertia, so it resists changes in motion. And so when the accelerators, or when the elevator starts accelerating upward, it basically kind of pushes against your feet to get your body moving upward. And when the accelerator, or when the elevator starts accelerating downward, it does take your body a split second to catch up with it. The elevator drops away and your body, because of gravity, gets pulled down to match it. but there is that split second where it feels like the floor is dropping away, because it really is. So as it turns out, if an elevator, if you were to say stand on a bathroom scale in an elevator, then when the elevator is accelerating upward, you feel heavier. And in fact, the bathroom scale would say that you are heavier. The number on the scale would actually jump as the elevator is accelerating upward. As if you were standing on a scale and the elevator accelerated downward, you feel like you're lighter for a moment. And in fact, the scale would agree. The number on the scale would actually drop. But once the elevator reaches a constant speed, everything sort of comes back into equilibrium and you feel like you're your normal weight again. And in fact, the scale would agree with that also. So if an elevator is accelerating upward, your apparent weight, that would be the weight registered by the scale, is actually greater than your actual weight. Your actual weight being your mass times gravity. If the elevator is accelerating downward, your apparent weight will be less than your actual weight. And once the elevator reaches a constant velocity, your apparent weight should be the same as your actual weight, assuming that the balance is calibrated correctly. So what we've got here, we can do some calculations to figure that out. We have an elevator with a 75 kilogram man, about 165 pounds, standing on a bathroom scale in the elevator. And we want to calculate what the scale reading should be. In other words, what is the apparent weight of the person if the elevator accelerates upward at 1.20 meters per second squared, or if the elevator is moving upward with a constant velocity of 1 meter per second, or if the elevator accelerates downward at 1.2 meters per second squared. So before we do any of those, we want to draw a diagram. So we've got our elevator here, and there are a lot of forces acting here if you want to really get comprehensive about it. You've got the tension in the cable that's holding the elevator up. You've got the force of the person pressing downward on the scale. You've got the weight of the scale itself pressing downward. You've got a normal force of the elevator pressing back upwards. And let's see, you've got the weight of the person pressing down on the scale. And the weight, yeah, and the force of the scale pressing back up on the person. You've got the weight of the elevator too. That gets, I mean, that's a lot of forces to account for. It would be much better to define the system as being just the person, and then it gets a lot simpler. Particularly because we don't have information on things like the weight of the elevator. Nowhere up here does it say what the weight of the elevator is. So we really kind of have to define the system as being just the person, because then the forces of interest are reduced to just a couple of forces, and they're things that we know. So if we call the system the person, then we have the person's weight pressing downward, and then we have the force of the scale pressing back upwards on the person. And you can look at it like this: weight pressing downward and force pressing upward, with the dot representing the center of gravity or the center of mass of the person. And because the forces we're interested in here are predominantly vertical, then you might as well use the standard X, Y axes. And it's going to be the Y axis that we're most interested in. At rest, or in motion at a constant velocity, the scale should read with the person's actual mass, which would be FP in this case, the force of the person pressing down on the scale. Or sorry, did I say mass? The person's actual weight, which would be FP, the force of the person pressing down on the scale. The forces acting on the person, which is the system in this case, would be his weight, that's W, and the upward force of the scale on him, which would be Fs. And in mathematical terms, that would mean that Fp is equal to negative Fs by the third law. So the magnitude of Fp and Fs should be the same, but they point in opposite directions. So Fp equals negative Fs. And what we need to do is find Fs to find out what the scale reads at any given moment. In order to do that, we can take F net, that is the net force on the person, which would be equal to MA. And we also know that F net would be Fs, that is the force of the scale pushing up on the person, minus W. And so that means that Fs minus W must be equal to MA. If we want Fs alone, that's going to be Fs equals MA plus W, because you can take the W over to the other side, but you need to change the sign. And W, of course, is mg. So that means Fs is equal to MA plus mg. And this is in terms of magnitudes, because that's what we really care about here, rather than not so much directions. And so Fs is mass times acceleration of the elevator plus mass times gravity. The mass is the person's mass. And so in part A, Fs is going to be 75 kilograms plus 1.20 meters per second squared plus 75 kilograms times 9.8 meters per second squared. And when you work that all out, Fs is 825 newtons. That is the person's apparent weight under these under acceleration upward at a rate of 1.2 meters per second squared. That's the apparent weight. This is actually a general equation for apparent weight when there's acceleration in the y direction. Apparent weight is equal to mass times acceleration in the y direction plus mass times gravity. Mg being your weight, so it's basically your weight plus the any extra apparent weight due to the acceleration. And upward would mean positive acceleration, downward would mean negative acceleration, as we'll see in a moment. Now, for part B, if the elevator is at constant velocity, that means acceleration is 0. So the Fs, or apparent weight, is 75 kilograms times 0 plus 75 kilograms times 9.8, which is 735 newtons. And that is the apparent weight at constant velocity, which is also the person's actual weight. And remember that constant velocity includes 0, so you get the same result if the elevator were sitting still. Because what really matters is that acceleration is 0. On the other hand, if the elevator is going down, that is, acceleration is minus 1.20 meter per second squared, then Fs is going to be 75 times minus 1.2 meters per second squared plus 75 times 9.8, and that's going to be 645 newtons as an apparent weight. So you notice when the elevator is accelerating upward, you have a larger apparent weight. When the acceleration is downward, you have a smaller apparent weight. And at constant velocity with no acceleration, you have a middling value, which is the actual weight. So your sensation when riding in an elevator is correct. You do basically get heavier, at least apparently heavier, as it accelerates upward, and apparently lighter as it accelerates downward. Another interesting case here actually would be, what if the elevator's cable broke and the safety brake that's supposed to stop the elevator from free fall fails, and the rails for the elevator were only just lubricated yesterday, so they're nice and slippery, and the elevator descends with an acceleration of 9.8 meters per second squared. In other words, it's in free fall. Well, the apparent weight would be, again, MA plus MG. And A in this case is negative 9.8 meters per second squared. So you would have 75 times negative 9.8 plus 75 times 9.8. Or in other words, 735 minus 735, or 0. So if the elevator were in free fall, you would effectively be weightless. Until it hits bottom. Then there's a very sudden deceleration and all that weight comes back to you all at once. That's the part that's not so fun. It's not the fall that gets you, it's the sudden stop at the end. Okay, one more example is the example of two attached blocks. This is what I was mentioning was going to come back in the next chapter to haunt us, and here it is. You've got two blocks that are attached via a pulley. The table is frictionless. The pulley is also assumed to be frictionless, and the mass of the cord and the pulley are considered to be insignificant, which makes the problem a lot easier. And you've got one block, the block labeled M1 on top of the table. Remember, the tabletop is frictionless. And M2 hanging over the side. All right, M1, if you want to draw your free body diagrams, M1 has a certain weight, which is pressing down on the table, and the table presses back with a normal force. And also there is a tension in the cord that attaches it to the other box or the other block. And so you have the mass and the normal force balancing each other out because the block is not accelerating up or down. And you have the tension pulling it toward the right. The block labeled mass 2 has a weight that's pressing downward, and it also has the tension pulling it upward. And those are the only forces involved on block M2. And the tension in the cord, in this case, does not balance out the weight. So there will be an acceleration downward for block 2, and that results in an acceleration to the right for block 1. Okay, and in true free body diagrams where you use a point for the center of mass of the object, this is what the free body diagram for block 1 would look like, and this is what the free body diagram for block 2 would look like. In this case, we can find the acceleration of the blocks and the tension in the string in terms of mass 1, mass 2, and g, that is gravity. And like I said, we can ignore the mass of the string and the pulley and assume that there's no friction. And the second law, Newton's second law, F equals ma, applies to both blocks. So in other words, F net equals ma. That's Newton's second law. For block 1, F net is equal to the sum of all the forces on the block. So the force of the tension plus the force of the weight plus the normal force equals the mass times acceleration of block 1. That's F net. Okay. For block 2, the tension, the force of the tension plus the weight of block 2 would be the net force on block 2, and that equals the mass times acceleration for block 2. The tension should be the same for both blocks, because in a situation like this, the tension is normally the same throughout the entire cord that connects the objects. That's assuming no friction, and assuming the cord doesn't stretch or bunch up or anything like that. So you can just write the component equations for each block. For block 1, we're concerned about the x direction because it's sliding toward the right, toward, horizontally. And so the summation of all of the forces in the x direction should be equal to the mass times the acceleration in the x direction. In this case, the summation of all of the forces in the x direction for block 1 would be just the tension in the x direction. And that's because the weight and the normal force cancel each other out. Well, they're in the y direction anyway, but they cancel out, so they don't really enter into anything here. And again, we can tell that the weight and the normal force must cancel each other out because block number 1 is not accelerating up or down. If there were a net force in, if these two values did not cancel each other out, there would be a net force in the up and down direction, and that would cause an acceleration in the up or down direction. Let's see, for block 2, the summation, we're interested in the y direction since block 2 is moving up and down, but not from side to side. And so the summation of all of the forces in the y direction would be equal to the mass times the acceleration in the y direction. The summation of all of the forces in the y direction would be the difference between the tension in the y direction minus mass times gravity, which is the weight. And that's equal to mass of block 2 times the acceleration of block 2 in the y direction. Okay, if block 1 accelerates to the right, that is the positive direction, then block 2 accelerates at the same rate, but downward, which is the negative direction. So in other words, A1, that is the acceleration of block 1 in the x direction, is equal to the negative of the acceleration of block 2 in the y direction. So we're just going to call this A for simplicity. And we also know that the tension has to be the same throughout the entire wire or cord or whatever it is. And therefore, Tx equals Ty, and we're just going to call that T. Okay, so going to block 1, we have tension is equal to mass 1 times A, which we're calling the acceleration. And for block 2, we have tension minus mass 2 times G equals negative mass 2 times A. And combining these equations together, since T is equal to M1 times A, we can substitute that in for T in the second equation. That is M1A in for T in the second equation. And we get M1A minus M2G equals negative M2A. Rearranging this a little bit, let's see, take the term involving the G over to this side and take this term involving the A over to the other side. So we're getting all the A's on one side and all the G's on the other side. We end up with M1A plus M2A equals M2G. You can factor out the A to simplify things a little bit. So A times M1 plus M2 equals M2G. And to solve for A, you divide both sides by M1 plus M2. So A equals M2G over M1 plus M2. And to factor out G, you get this, M2 over M1 plus M2 times G. Essentially, this and this are the same thing. It's just you factored out the G. All right, you can then rearrange again to solve for T. If T equals M1 times A, like it is up here at the top, then we just found out what A is. A is this or this. And so T would be M1 times this. Okay. And then when you multiply it out, it's M1 M2G over M1 plus M2. You again factor out the G and you get M1 times M2 over M1 plus M2 times G. Okay, so we have acceleration, and tension. And you could work it out like that in any problem like this, except that in most problems you would have numbers. And so you could just insert the numbers in and get a number for the answer. Okay, well, that's all we have time for right now. And so I'm going to cut it off there, and we'll come back with the Atwood machine next time.